the first speaker will be Jerome Revaud. I'll give like a three-sentence introduction. Jerome Revaud is a research scientist, or maybe senior research scientist at Naver Labs Europe. He works on 3D foundation models in 3D vision, which I believe are very applicable to the robot world models domain. He is one of the co-authors on seminal papers like Croco V2, Duster, Master, Muster, I think, which is more recent, Power, in general, a bunch of really exciting 3D foundation models. So I'm excited to learn what he has to say today. And Jerome, please, if you can share your screen, we're excited for your talk.
Thank you. So yeah, today I want to talk about the 3R family, a foundation model for 3D vision, or actually a candidate. So in this talk, I will first present where I'm coming from and like my background, the place where I work, and the vision of our lab. And then I explain what my definition of a foundation model for 3D vision is. And essentially, the Duster framework is the answer to this question. So I will present the Duster framework from the pre-training up to the training and to recent extensions. And I will conclude with some final remarks. So Naver Labs is a company which belongs to Naver, a Korean IT company, pretty much like Google, but in South Korea. And Naver Labs is really focused on robots. So Naver Labs built a huge building in South Korea where robots and humans can cohabit. And here you can see one of these robots, which are right now delivering parcels, drinks, food. And so users can, like anywhere in the building, you can order something, the robots will bring it to you, it can navigate, it can take the elevator. But this is like a giant test bed for robotics. Right. And I'm working in Naver Labs Europe, which is located in Grenoble, France. This is a really nice place. If you can visit, that would be wonderful. And we really focus on making robots part of our everyday lives. And for that, we undertake a multidisciplinary approach to AI. So I'm a computer vision guy, and I come from the 3D vision field, more specifically. And for this 3D vision, what is it? I would say that it's a collection of different tasks, like, for instance, monocular depth estimation, large-scale 3D reconstruction, point matching, visual localization, multi-view pose estimation. You name it, right? There is a lot of 3D vision tasks. And the commonality between all these tasks that somehow they are all dealing with 3D geometry, camera positions, these kind of things. So far, these tasks have been treated separately, with very dedicated and specialized approaches. And this is really a bit problematic, right? It's not very satisfying because they share a lot in common, yet they are treated with completely different approaches. And if we look at the case of the natural language processing community, it used to be the same. There used to be many different tasks like translation, sentiment analysis, text summarization, question answering, and so on and so forth. And of course, we all know what happened with ChatGPT. Basically, a single model can pretty much zero-shot solve all these tasks. But not only it can solve all these tasks separately, it can also solve any combination of these tasks. And that's really game changer and opens like so many use cases and possibilities, right? So foundation model is I think something we should definitely seek, but there's no real consensus, no real definition of what a foundation model for 3D vision is, right? Here is a non-exhaustive list of proposals, and all of them have some kind of different definitions of what it is. I think everybody agrees that it should be at least like pre-trained with some kind of weakly supervised pretext tasks, like next token prediction is really useful for downstream tasks in the NLP community. So basically, my take of what a good foundation model for 3D vision should be is basically a model able to establish correspondences between images, able to infer 3D geometry, either from learned priors, like for instance, in the case of a single image, or from multiple views, like triangulation or something like that. And it should also be able to infer the position of the camera. It should be able to decompose motion, lighting effects, long-term changes. And this leads us to our first work called PROCO. So PROCO is short for self-supervised learning with cross-view completion. And PROCO is a guessing game. It's a very simple game. Given two images, right? We have a reference view and a query view, but a part of the query view has been masked. And the goal is to predict what is hidden behind the mask. And to solve this task, well, you're going to compare the two images, right? You're going to do image matching. You're going to need to estimate the relative close between the two cameras. And for that, you need some estimation of the depth in the image. You need some priors about shape, like this stone pole has some flat surface with some kind of shape we kind of understand. You need maybe to adjust the color changes because the lighting conditions are different. And if you do that all of that perfectly, then voila, you should be able to accurately predict what is hidden behind the mask. So that's exactly what the pre-training PROCO is. So basically, we have this two input views of the same scene, and the query view is randomly masked. And in the middle, we have this big transformer network. So VIT's vision transformer is basically a vanilla transformer that takes patches instead of text tokens. And it outputs, the query image unmasked. And it's trained with a simple L2 loss in the RGB pixel space, right? So when you train such a network on millions of pairs, image pairs, either synthetic or from real data, then this is what you get. So on the left, you have the two input images, and here you have the output, and here the ground truth. And you can see that it's a bit blurry, but definitely it looks like it gets it right. And here, for instance, this brown object is completely masked, but it's still able to infer its existence because it's in the reference view, even though it's a bit blurry, meaning it's not very confident about exactly where it is in the scene, right? And we essentially built on top of PROCO to build Duster. So Duster means dense and constrained stereo 3D reconstruction. And this is the same architecture, right? It's exactly the same, except that this time, instead of predicting RGB images, we are predicting point maps. And point maps are explicit 3D representation of the input image. So specifically, the point map is an image, but instead of RGB value for each pixel, you have the X, Y, Z coordinates for this pixel, right? So this is what is represented here as blue dots and red dots. These are point maps. And to make the problem well posed, we defined these 3D coordinates in the reference frame of the first image, assuming it has an identity code. And we apply, again, a very simple regression loss, which is scale invariant, because the scene is known up to a scale factor, right? And again, when you train Duster on millions of image pairs, again, synthetic or from real data, we use typically a mix of both. Then it works, the same model works indoors, outdoors, on close-up objects, on any kind of data. And it even is able to perform tasks that were not possible before. So this impossible matching task is given two images without any overlap. There's not a single pixel shared between these two images. yet Duster is still able to construct like the correct reconstruction because it has learned many pointers. Like it knows that the ceiling should be aligned, the wall should be aligned. It understands that this is the left, like this should go on the left and this should go on the right because maybe there is a bit of a table here and the other side of the table here and so on, right? So Duster, we actually extended several times. So the first extension we did was with master. It's basically a very simple extension to improve the matching accuracy. And then we were able to solve a hard problem, like hard for a human at least, like this. Given these two images, what is the relation between the viewpoints? It's kind of hard to tell, but actually this pool here is the same as this one, and the viewpoints are opposite, right? And when we apply master on this kind of hard image pairs, we get like really amazing results, like much better than existing matching approaches. Like so good that actually we won the map-free verticalization challenge by a large margin. We got like 80% precision, and the second best was less than 50%. This was last year at ECCB. Right, and here is a like visual demo of, so in red you have the reference image and the query image is the moving camera. And all these frames are treated separately. There's no temporal smoothing or aggregation, so it's kind of impressive in my opinion, right? And when applied the same model to multi-view stereo, which is like dense 3D reconstruction, we can actually beat handcrafted methods, and we perform on par with in-domain, like dedicated approaches for this task and for these data sets. And we actually perform on par while, this is zero shot. We have never seen this data during training. So again, this is like a clear demonstration, like foundation models have this like capabilities of zero shot outperform any dedicated approach. And we further extended master with master SFL. And Bart was one of the authors on this paper. We got the best student paper at 3DV recently. And very quickly, this is like the kind of dense reconstruction we can output from very few images, which I think at the time of submission, like not a single approach we're able to do. So to summarize, the Duster framework, we made 3D vision easy, at least we believe so. It takes an unconstrained collection of images, and constrained means no pose, no intrinsics, and it output point maps, which are essentially dense 2D, 3D mappings. And from these point maps, we can extract, straightforwardly many things. We can recover the camera calibration. We can get depth maps, like from monocular case, for multi-view cases. We can get pixel correspondences, camera poses, and then 3D reconstruction. So is that the end of it? Well, of course not, because there's many like real use cases where, for instance, you would have specialized sensors. You have a camera rig, like this case is a straight view vehicle that collects straight view images, and it has LiDAR. So how to use this additional information? Well, Duster cannot. It just take images as input. Same if you have a robotic arm, you have these two cameras. One of them is still, one of them is attached to the arm. I'm sure you have calibrated very properly your cameras, and so basically the question is how can we incorporate additional information into Duster? This is the our paper we recently presented at CVPR. And yeah, I think I already explained the motivation. So the idea is very simple. We start from the Duster architecture, but this time during the training, we optionally, provide more information to the encoder and the decoders. So randomly, we input intrinsics, depth, which can be sparse, can be dense, or we also provide relative terms between the cameras. And because this is randomly selected at test time, the network basically can deal with any combination of information. And we verify that if we just give like images, exactly like in Duster, it performs as well as Duster. But if we provide more information, like the intrinsics or the relative pairs, then it starts predicting like much better results, which makes a lot of sense, right? And not only this is already nice to have improved results if you know the calibration, but you can also do more tasks. Like for instance, here's something we could not do with Duster. So here you take two images, you put them in Duster, you get some like force reconstruction because Duster works with like fixed size resolution. You can extract the depth maps from this first output and can re-inject that, this time in a sliding window mode, because sliding window is actually parameterized by intrinsics. So for each window, you can specify the parameters of the crop based on the input intrinsics. And then you can, this is the raw output actually. It's basically doing some high resolution reconstruction, in a tiling, like sliding window mode. And it can, for instance, also do depth completion based on like sparse LiDAR points. So here, this is the new NYU datasets. You have an input image, and you have sparse like depth points. And because the method is trained to always output dense outputs, then we get the dense depth map for free, right? And we actually outperform every existing like specialized, again, like the dedicated method for this task, which is called depth completion. We outperform this zero shot. So far, the Duster family or 3R family, we have leveraged large-scale self-supervised training with Croco. We show, I didn't talk about that by lack of time, but we show that this is important to have good performance with Duster and all following works. We made 3D vision simple and flexible, right? All tasks are now covered. But one thing I forgot to mention is that all of that is offline, right? And Naval Labs, we work on robots, but robots live in the present. So we need some online real-time processing, right? That's the last work we have presented last week at CVPR. And the idea of Mooster is basically to extend, Duster or Master to some online mode that can also handle videos and basically process images one by one. So again, we start from the Duster architecture. And if I expand the decoder block, which is when the transformers from the first stream and the second stream exchange information, they are composed by a succession of blocks, transformer blocks, with self-attention, cross-attention, and MLT, right? And the cross-attention is here to basically exchange information. So the first stream, is sending its token to the second stream, which is going to incorporate this information, and it continues like that several times. So if we remove one of these errors, we can basically make this method causal in terms of the temporal direction, right? Let's imagine these are frames, frame 1, frame 2, frame 3, and so on. Then this architecture becomes causal because this transformer is only relying on previous frames, not on future frames. Meaning now it becomes basically an online method. So we can train this, right? And this becomes the same decoder. These decoders have shared weights. So in a sense, what we end up with is this very simple architecture where we have an input frame it goes into the encoder, and the decoder compares this frame with some latent memory, which basically contains the previous frames, and it updates the memories with this new frame. And also it outputs, like a 3D, like a point map for this frame in local frame and also in the global frame, which is defined by the coordinate system of the first image in the sequence, right? So here is a demonstration on a small GPU running on the laptop. This is real time. You have the reconstruction here, and on the right, you have the input video, right? And this is basically the raw output of the method. So you can see that, yeah, it's kind of impressive in the sense that there is not a single optimization, like, geometric explicit optimization here. It's pure feed forward. There's no bundle adjustment. It's pure regression, right? There's nothing else here. And it's basically doing loop closure in an implicit manner because of the memory, right? When it comes back to something it has seen in the past, then it has to basically fall back on its feet. Again, Muster works for any situation. It works for like large scale outdoor scenes, indoor scenes, like close-up objects, and so on and so forth. And it even works on really large scale. I mean, it's not city scale, but it's still quite big. So this is 400 square meter indoor space in a chateau. We have a chateau here at Naval Labs Europe, castle, French castle. And you can see the camera is navigating inside. And this is like the real-time output of Muster. And it's a bit noisy. It's clearly not perfect, but the blueprint is correct actually. And yeah, I mean, to my knowledge, this is the only method that can do that in a feed-forward only manner, right? I know SLAM methods nowadays can definitely do something like that, but SLAM is quite handcrafted a lot, right? And so the nice thing here is that this is pure data-driven, and I'm sure we can further improve on that. So of course, there's a lot of recent works that have expanded the 3R family. There's Spanner also from 3DB. There's Qter, MPDuster Plus, Faster, MasterSlam, Monster. There's the large spatial model, and Raster very recently, where the extension of Duster to predict like the front and back sides of objects. I'm sure there is many more that that are listed here or that I forgot. I'm sorry. So yeah, to conclude, I think Duster is a good candidate for 3 foundation model. It unifies 3D vision tasks. It unifies offline on online tasks, unordered image collections and videos. Of course, there is some remaining problems like semantics. Of course, we need semantics if we have a true foundation model. And accuracy is not yet as good as ColdMap in some situations where you have like lots of images with lots of overlap, lots of texture. And for sure, we are not at this level yet. But I think the gap will be closed soon. And these are very exciting times for 3D vision. So thank you for your attention. And please, if you have any questions, don't hesitate.
Thanks a lot, Jerome. That's a really awesome presentation. Are there any questions in the room? I can bring the microphone to you if you're interested. Okay. Jerome, can you hear this?
Yeah, absolutely.
Yeah. Okay. Yeah.
Hey, thanks a lot. One thing that you did not talk a lot about was actually like the underlying data that you require to train such models. Like,
Right.
Can you say a few words around this? Like, how important is the data? How much curation did you do? Like, how did you go about this?
Yeah. So there's 2 aspects of this. the pre-training, for the pre-training, this is like a self-supervised task. So you only need to find pairs. And it's kind of easy to make pairs from like, using existing handcrafted approaches. And it's not a big issue if your pairs are sometimes wrong but for training Duster and all subsequent models, we found it was quite important to have like high quality data. And it's true, I didn't really talk about that, and this is a very important aspect. So what we found is that data is really important, right? That's the most important criteria in Duster working well is the quantity of data. That's one thing. Second is that we found it's good to have 50% of synthetic data and 50% of real data. So synthetic data are like really perfect in terms of ground truth, and they serve the model to learn really accurate predictions. Especially, real data, you typically struggle with annotating thin structures or, corners and like edges, these kind of things. So synthetic data are great for that. But with only synthetic data, you have a trouble generalizing to the real world. So having a mix of 50% synthetic and 50% real data is, I think, is a good trade-off. And one last thing is that recently, there is a lot of new data sets about like 3D like scenes. There is mega scenes which contain 1 million landmarks. There is a 361M, which also is like 1 million 360 videos. So there is maybe not such a need to have like unsupervised training. Maybe it's fine to massive like fully supervised training right now. I'm not exactly sure, but I have been quite surprised by the recent surge of like large scale data sets in the last year.
Right. Thanks a lot, Jerome. I think we'll move on to the next speaker, but thank you so much for giving the talk.
Thank you.